Okay.
Thank you. Really sorry about the delay, everybody, and thank you so much for inviting us over here. So, as most of you would have read this by now, well, can knitting really be more useful than sweaters and scarves? I guess we had the same question. And so today we'll be sharing our research project Knitectonics, which commenced at the DRL in 2010. The agenda of the proto-design investigated analog and digital forms of computation in pursuit of prototypical applications. Materials and production processes perform as active agents to accomplish an architectural approach that is both adaptive and hyper-specific. Here are some of the other projects which were done in the same studio. The project premise for us was to re-engineer standard design and construction processes to achieve economy of means. Economy of means can be defined on many parameters. Our research initiated with the study of monocoques. Of course, we have the master here, Professor Michael Stacy. Monocoques can be defined simply as single shells where the skin is the structure. And in nature, we see how a simple egg achieves extraordinary efficiency using the same principle. In the man-made world, a can of Coke is the simplest example of a monocoque. Concrete shell structures by Felix Kindela and Heinz Eisler are the most exquisite examples of monocoque structures in architecture. However, the use of shell structures declined over time due to elaborate formwork required. So the challenge for us was to identify a new fabrication system which was beyond the limitations presented by the current construction technology to build monocoques. While studying the biological machines, we observed that it's difficult to emulate complex yet efficient biological forms for us humans, because unlike our rigid construction system, in nature things are manufactured molecule by molecule. Self-structuring is nature's strategy to build economically in terms of material, energy, and time. By extrapolation, in the man-made world, self-structuring forms could be achieved by employing a continuous fiber, so the material could be placed optimally where it is required. Here are some of the initial experiments we did to achieve structural skins with fiber and matrix materials. The inference was that structure can be further optimized by differentiating fiber distribution and density, similar to textile techniques. Textiles have often coincided with architecture in history, and today they are predicted to be at the core of a revolution in architecture. German theorist Gottfried Semper located textile as the first technical art, and recently architect Peter Testa proposed a 40-story high carbon fiber textile prototype. Lasspie's book further talks about soft elements becoming rigid using various processes used in textile industry for mechanically manipulating fibers into textiles. We studied all these different methods, but all of them required formwork. Only the technique of knitting had the desired attributes. Continuity of material enabled us to create structures without formwork, and the formation of one loop at a time gave us the opportunity to explore complex forms. So using fiber as the material and knitting as the method, we proposed the metaphor of economy of means. And then began the exploration of knitting. Knitting simply can be described as a method where one-dimensional yarn forms loops and many loops together form a two-dimensional fabric. Knitting machines use the same principle as hand knitting, and the machine we used is a circular knitting machine, and the two basic topologies we could do with the machine were cylinders and flats depending on the direction of knitting, if it was circular or it was alternating. Well, most of the things we learned from our analog experiments were pretty much obvious for grandmothers or textile designers or knitwear designers, but not for us. For them, each of them was a eureka moment. So we started experimenting, doing crazy experiments, mixing a lot of different fibers to study flexibility and rigidity, as you see here. And then with different loop sizes to study porosity. And then we started mixing the topologies of the cylinders and the flats to try to create holes and bends within the same knitted fabric. The inference was that topology, density, and rigidity of the knit output are dependent on the parameters of machine size and shape, yarn type, knot size, and tension applied. Of course, we would like to mention here that we didn't expect sweater to become architecture, and we had to do a lot of additional processes to gain rigidity. So all these models that you see here have been impregnated with resin to make them rigid. But with all the analog experiments that we did, we had a lot of limitations. But our ambition to add complexity to this system pushed us to start knitting digitally. So the first tool that we developed digitally was the decoding tool. We simulated the material behavior using the processing platform with physics and the Toxilix library. Here we see multimateriality and creation of punctures. And we also tried to do different loop sizes to test porosity. And next we decoded the knitting based on the machine rules and simulated the knitting action. Now each of the dots here you see is representing a loop. The orange ones represent knitting continuously, and when you see the green ones, because it's alternating and it creates flats. To get a more realistic approach of that, we had to impart tensile forces into that fabric to understand what it is realistically. And then we started simulating a lot of crazy rules, and we had a lot of sort of unpredictable outcomes. And everything that we couldn't knit analog now, we could knit digitally. Then we simulated multimateriality and surface patterning, which could inform us on aspects of structure, and also the machine action, which could aid us in understanding morphologies, openings, and rigidity. Next was to combine the analog and the digital, and we converted our machine to a CNC knitting machine, which could take digital information and knit. For this, we had to hack the machine in two aspects. First, we had to make the mechanical knitting electronic using a G-code, and the second was to control the needles digitally using an Arduino microcontroller. So to validate our argument of strength and potential of fiber composites in knitting, we did this test where there was a simple shell which weighs 100 grams, and it was made with one continuous yarn, but it could take the weight of 700 times more than its own weight without collapsing. The structural validation, along with the understanding of rule systems and ability to program knitting, brought forth the evidence that the everyday craft of knitting could indeed facilitate the possibility of an integrated proto-fabrication system. Now, typically, the machines in the textile industry are for sweaters, and they are for a scale of the body. To adapt the system into architecture, our primary concerns were scale and stiffness. We saw this instance of a lamp called Sleeping Beauty by Nadine Stark, which gave us the confidence that it could be scaled up. And to enhance the stiffness by layering, we started combining multiple machines of the same size. And then we projected further that if the machines were of different sizes, we could achieve hierarchy of spatial configurations and break the monotony of the single cylinders that we had till now. Theoretically, the idea of combining machines was ideal, but mechanically it was a nightmare. And here you can see two cylinders which converge into one, or at least they're trying to. So we went back to the 200-year-old knitting industry, and we took inspiration from patents done for textiles. This is a patent by Benito Manini for seamless pants. It gave us a new perspective because we realized that the textile being soft, if it's a closed loop of any shape, it will still give you a cylinder. And the other important the other important observation we had that the machine had a bridge which could be put on or off and at any point. So we had the choice of seamlessly connecting two tubes and bifurcating and then connecting them back together. So at this point, we knew that all our intuition was valid with respect to knit topologies, because mathematicians have used knitting to explain a lot of topological geometries, but we were not aware what was the most efficient way of combining them together. So we started with the off-the-shelf closed-loop circular machine. Then we switched to putting 2 connection points to it, which was still not enough for us. Then we went on to 4, but now we couldn't connect the diagonals. So we went on to 6, so we could connect them in 6 different points with a hexagonal shape. But again, we realized the limitations of the hexagonal tracks, and they were very difficult mechanically to manipulate, and the fabric, after it was knit, would get stuck between all the 6 loops. So we tried to resolve it mechanically by using the triangular interstice, which was formed between the different hexagons. And ultimately, we came back full circle to a circular machine. But this time, we had 6 connection points in the same circular machine. Now, further detailing our prototype, each of these machines has a fixed needle bed, as opposed to the old machine where the needles were moving. And the cam system in our new machine would be moving as compared to the old one where it was stationary. What we had additionally added was the yarn head, which would be moving on tracks and bridges, and it would become an independent yarn feeding agent. So using these conceptual machines, we created a digital interface, which we refer to as the design tool. Here, we have a single knitting track with 6 bed of needles and 6 connection points. The yarn feeder or the head drops particles as knots, which are connected with springs. Each row is knitted. The physical properties of the specified yarns in terms of elasticity, its strength, and weight are activated. All these functions that you saw on the left side were those ones. And then the interface allows us to design in real time. The idea of the bridge connection was that the yarn feeder could move on the tracks and it could jump to another track whenever the designer wanted, and it could create a longer external perimeter. All we had to do on the interface was switch on or off a bridge. And another thing, this way we could also drop needles or bed of needles, and we could create a lot of different topologies. Another important thing was that we were using gravity, whereas in normal machines you put rollers to pull the fabric. Here we were using gravity to kind of pull it and attach it to the ground. So we had all these functions of solidification, attachment to the ground, everything within the same interface. And here we went down to 3 machines because we believe that whatever you can prove for 3 works for anything. That's how we were creating the punctures, by sort of dropping the needles. And here you see all the different heads which are doing different things. And another interesting thing with 3 machines was that we could use the interstices between the machines to create almost forms on the surfaces which were the inside and would then become the outside, like a Mobius strip. This is how we were looking at connecting different machines. In the first one, you see what the machine does when it's knitting 1. Then you have 3 of them together, so the perimeter is bigger. And when you have all 6 of them put together, this is just one instance, but the bridges could be activated in many different ways. Following the organization of circular packing, which is the most efficient one, with 6 connection points, the machine could be arranged not just in the first hexagonal fashion that we were showing, but in many different linear configurations or in organic configurations. So it was very imperative for us to introduce the idea of machine of variable sizes, one which would form the spaces and the volumes, and the other which would create structural elements like layering, the elements which conform the envelope. So to determine the size of the machine, we calculated the thickness of the envelope. And it's very important to note here that once you knit something and you start pulling it, the enclosure that you have within the knit object is much smaller than the cylinder you created to start with. So with that in mind, we calculated the size of a small machine and the big machine. The variable sizes machines could be assembled together in many different fashions. And along with the voids which were created between them, they gave us a lot of tectonic opportunities to put envelopes, structural elements, and other service cores or shafts or infrastructure.
Yeah, at this point we needed to test the materials and test at a bigger scale. So we started working with Nottingham Trent University with Dr. Thiago. He was very excited about the project and kind of helped us develop a series of prototypes to kind of test our ideas on a linear machine that we can later solidify. This is another model using the idea of 4 machines with different bridges activated at various points of time, creating enclosures and openings. And this kind of series of tectonic elements, developing a few possibilities of columns, 3 tracks, 4 tracks, 5 tracks, kind of understanding the tectonic aspects of the project. Openings, same idea, the punctures by dropping the bridges. And kind of start thinking of how we can approach the tectonic aspect of this if it becomes a building, how to connect to the ground, how kind of typical slab detail is, a roof detail. And at this point we also said, okay, everything cannot be knitted, we have to have a mix of systems, have honeycomb panels, and just start mixing up to kind of make this architecture possible. This is a model. Actually, this was quite an interesting point for us because this was developed separately. We had agreed different parts of the teams of kind of develop the digital and the analog. And the results were quite similar, although it was done in 2 separate places. The model can be seen back there. We'll bring it up later for the questions so you can see it. It's a section of the shell. And it's kind of the porosity of the elements. The nice thing about the potential materials with our system could be the advantage of techno-textiles available and all the developing things. Monosystems that can be combined as a multiple materials, which belong to 3 families. We call them kind of structural, infrastructural, and performative materials. Okay. We identify kind of this series of elements, like we think, okay, what the materials we need if we're going to deploy this and build a prototype. We define a pre-impregnated kind of carbon fiber or other resistant fibers that can be knitted. Ternara yarn for kind of soft elements, silicone, of course, to kind of create a vapor barrier and control water coming in, flexible organic cells, silicones, all kind of systems you can embed into a fabric, and kind of the potential of the structural capacities of kind of textiles. You can even done composites. Even we heard that in the 70s somebody tried to do a knitted airplane, although we couldn't find any information about it. Parallel to the knitted process, the solidification is kind of key to a process, and how to accelerate this process of these pre-impregnated yarns. We think about two rings. One is the ring that knits on the top, and there's a secondary ring on the bottom that is kind of a UV lighting, kind of to accelerate the process of the solidification of the knitted fabric. The distance also, this is important for us also, out to the point, is like, digitally we can knit wherever, but at one point we have to tell the system, you have to break at one point. You cannot just keep kind of stretching the system all you can. So we had a point where the knitted fabric that is digitally be done would break. And we needed to know, okay, at one point we can calibrate this kind of model, so we can develop a series of model to kind of start calibrating the script. This is an idea, the first idea of the deployment we had in focus. We follow the 6 stages. The first is the machine setup on site. The second one is kind of a crane that's need to be lifted up from the ground, possibly with a crane. And then the attachment ring at the bottom that kind of allows to attach the fabric. The fabric gets attached, and the solidification ring kind of starts solidifying the knitted fabric. The deployment process brings us back to the analogy of nature, of the motion. As we evaluate our machine against the biological model, the motion top-down approach is translated in the setup and procedures of our machines. You can observe how the small machines along the perimeter knit the envelope, and the bigger machine that forms the usable space inside. It's kind of, that was a very nice moment of us to come back to the initial inspirational moment. To understand kind of the prototyping, the deployment of this, we used 3 real scenarios. There was a proposal for a PRT system in the city of Bath, a city of 80,000 with 4 million visitors a year. We selected 3 stations because of 3 different scales, and on these 3 stations, we decided to test different things that could happen with the machine deployment. This is kind of some ideas of the scale, understanding, and the type, the use, the sizes of machines, the speed and the process. But we're going to focus only in one scenario today, that is the George Street. So basically, it's a simple canopy station that comes from the ground, all on the ground, and then here you have 3 machines being deployed, 3 big ones with little ones around. The crane kind of starts lifting up the machines. And the nice thing about this simulation is that we have the physics embedded in this whole. So it's not only animation, it's like it's happening as we see it right now, and we can control where the heads go and kind of knit with each other. And it's nice to find that point of equilibrium of one head pushing the other head kind of to find the form that's coming along. And that was quite critical for us because it's a little bit like this validation of what will happen in real time. Here we remove the machine so you can see the heads. And each of these different colors represents a different materiality, different aspects. The blue ones we think, okay, let's say blue ones would be structural, white could be like systems, and then the other one could be like another embedded behavior to the materiality. Okay. So this is kind of the final outcome of this kind of prototype element. Here is on the graphic on the corner, you can see one single yarn, kind of the path through the whole element during this abstraction. And this is the section, next one. The flow pan, kind of the deployment system. And this is an interesting point, is like we have 4 sequences that we have 0, 1, 2, and 3. 0 is when it hits the bridge, it goes back. Sequence 1 goes back and forth. Sequence 2 bridges, and the last option, sequence 3, is cross bridging. Based on this, you can have endless possibilities. So you start asking yourselves, where do we go from there? So we start looking at all the possible variables. We have number of tracks, number of yarns, number of heads, yarn properties, start position, and heat sequences. So at that point, we decided to start playing a little bit with a genetic algorithm to kind of start telling the genetic algorithm, you learn from the system and you choose what to do. So we have 2 basic premises. One was the structural point. As I said, we calibrated the system to kind of break at the point that it gets stretched too much or is understretched. And the other aspect we do is, okay, we're forming space, so we need to validate kind of the space we want to have inside. So at this point, we have the genetic algorithm kind of working itself. And so each time we have 100 random combinations of these parameters, and then we selected the 10 fittest options. Then we breed each other to the next generation of options to breed another 10 generations. Until at one point, we start finding a balance in the system, and the balance systems are saying, okay, based on these two premises, that's kind of your most optimal selection of yarns. At the end, we kind of found this result, okay, this is your most optimal structural space solution from all those 100 generations you have.
So to conclude, we of course started with physical experimentation, but as Alan had mentioned yesterday, that prototyping is also, digital prototyping is also a way of prototyping. So we were doing digital prototyping, which is all the time informed from all the analog experiments we did. So here we are starting with all the kind of different things which were available to us when we were doing the analog experiments, and what is the sort of route we took. And then we come from the other side of the digital prototyping and then see how they kind of come together. So to conclude, with Jacquard Loom, the pre-designed technique through pre-programmed instructions gave way to computation. And our three tools use computation to design, visualize, and instruct, and fabricate in the real time. These are our first steps in research and development of a knitting-based parametric system, but we believe that this sort of a prototyping system can be applied to any other machinic process. Thank you very much.
Thank you.